Welcome everybody, and thank you for joining our webinar Introduction to Analyzer 2 and EEG Analysis Concepts. My name is Michael and I'm happy to be your presenter today. With me are my colleagues Kidis and Michael as moderators. Before we start, what are the intended goals of this webinar? First, we would like to get to know BrainVision Analyzer 2 with its main concepts, functionalities, how to navigate through your data and how you can inspect it in more detail. Secondly, I would like to give you some orientation about EEG analysis, covering different aspects like paradigms, different signal domains, and processing techniques. By this, we would expect you to get familiar with the workflow in Analyzer and making use of Analyzer's functionalities for great data processing experience. For many research questions, you should get an idea which way to further investigate regarding the analysis concept you would need. To do this, what is our outline of today's session? In part 1, I will introduce you to the Analyzer interface, including requisites and data format. I will discuss main concepts and views, as well as our well-appreciated automatic processing options. In part 2, I will first give an introduction to the various signal domains. I will talk about two main experimental design concepts, as well as about going from source to electrode space and back. The focus lies on the introduction of different analysis methods, what the basic concept is, why they are used, and what you get from them. At the end, we will have time for some questions, which may have come up during the session or you even had before. The webinar will be closed by some concluding remarks, including information on where to find more information about what was being said today. So let's start with some basics before we have a look at the Analyzer interface. Analyzer is able to read about 30 different EEG data formats. Please check our website for a list of all the readers which are implemented. No matter how your EEG data format is stored, as long as it is compatible, Analyzer will treat it as every format, so no conversion is required. As an example today, I used the native BrainVision format. When you recorded your data with Brain Products hardware, each recording consists of 3 files. The actual data is stored in the .eeg file. The .vhdr file is the header file. It contains information about the data structure. The VMRK is the marker file containing all the trigger event codes. Please don't change the name of these files because they are linked internally. So now let's start Analyzer. And for that, I will quickly close my slides. After default installation, you will find the Analyzer icon on your desktop. I have a dongle plugged in locally with a valid license on it. I start Analyzer. And it actually appears on the other screen, so I move it over for you. And when you start it for the first time, this is what you will see. As in most applications, you have a menu up here. This offers different functionalities, and we will go through it in a minute. The primary window here on the left is empty because no data is loaded yet. And here on the right, you see the online info page. This provides information about new updates or releases, webinars, and so on. Let's start the tour in the menu up here. Under File, you will find the workspace. This I will explain in a few minutes. As well as some printing and view options, you can also have some configuration options here. For example, you can change the appearance of the online info, which is, for example, under Preferences, the General tab, and you find the option Show Online Info at Startup, Never, or in case of important changes. I'm going to keep it as shown to Always. Next menu is Display. Here you can change or define the montage. Please note that this is not yet an operation in the sense that it changes your data. It just offers different ways of looking at it. Under the ribbon Skins, you can change the color scheme of Analyzer. The Transformations tab gives you access to the signal processing functions that exist in Analyzer. Multiple signal processing functions are arranged in dedicated group, like here in the segment analysis functions. Here you can find transformations like baseline correction, segmentation, or average. These are currently grayed out because no applicable data is active at the moment. We will explore some of the transformations later. Add-ins provide additional functionality. For instance, Analyzer Video. Bear in mind, for some of these additional functions, you require an additional license. Under Export, we have access to multiple functions that allow us to export outputs from the computations performed in BrainVision Analyzer. For instance, under Multiple Export, you can export peak information related to your ERP waveform using Peak Information Export. Exports are usually stored in a dedicated export folder of your workspace. With macros, you have the possibility to program your own scripts to expand the functionality of BrainVision Analyzer 2. Macros are written in Sex Basic. This is an advanced option and will not be discussed during this webinar. Solutions are additional plugins that complement the functionality offered under transformations. Many of these allow analysis on a single trial level. As in the case of transformations, solutions are grouped according to labels, like the EKG, EMG, or the export group. For example, the solution peak export is useful for single trial analysis and to export different kinds of peak information in one go. Solutions are not installed by default, but can be downloaded from our website. Furthermore, if we release updates for solutions, these need to be applied separately. They are not updated with Analyzer releases automatically. History template is one of the most appreciated functionalities in BrainVision Analyzer. It gives you the possibility to define a sequence of processing steps and apply them to all datasets automatically. This is the automatic functionality that I will show also during this demo. Last but not least, in the Help menu, you can find important information. For example, you have direct access to the user manual, or under About Analyzer, you can see the currently installed version of Analyzer, or check out your additional licenses. Now that we had a quick overview, let's load some EEG data to get familiar with the concepts in Analyzer. First of all, we don't have the option to load or import data when you look here under Workspace or File. We can load a workspace, but let's answer first, what is a workspace? The workspace is a configuration file, and this we are storing the path pointing to the dedicated folders of the raw data files, processing steps, and exports. Thus, before defining the workspace in Analyzer, we need to define 3 dedicated folders. For that, let me minimize Analyzer for a second. And we always recommend to store your data to a local place on your hard disk where you have full access rights. Here, put some data on the desktop. And in this folder, as you can see, we have 3 files in the BrainVision format. So every file consists of each subject recording consists of 3 files, the .eeg, VHDR, and the marker file. Subject 1, 2, and 3. To create the workspace and the workspace folders, I first create a folder and I call it raw data. Let me copy in the recordings of subject 1 and 2 for now. Secondly, I create a folder called history. For now, this folder remains empty. Only after first loading the raw data in Analyzer, new history files will be created, as we will see in a minute. As a third folder, I create export. Export also remains empty, but every time I use an export function in BrainVision Analyzer, the output will be stored here. Now I have everything to define my workspace in Analyzer. Before we go back, let me just copy the path here, and Analyzer should be open still. Here we go. So we are in File Workspace, and we want to create a new workspace. In here, I can paste the raw file folder, as well as the history folder. And also our export folder. I click OK, and I will be asked to save my workspace in a file. I call this webinar and save it as a VKSP2 file, the workspace file. As you can see, the raw data is now shown in the primary history file explorer. Clicking on this little plus sign up here for subject 1, I have access to the raw data. Double-clicking this data shows me the data in a dedicated view on the right here. On top of the view, we have this toolbar. Shortcuts here allow to inspect data in more detail. For example, you can change the number of channels shown, and you can also decrease or increase the scaling. The navigation bar at the bottom allows me to inspect the data throughout time. I can also use these buttons to go in smaller steps or in larger steps. You may have noticed down here our labels. These represent the markers collected during the recording, showing what was happening during the experiment. In this case, from an oddball paradigm, the markers were labeled standards and deviants. An indication of where markers were present throughout the experiment can be found as red bars in the navigation bar. This is down here. So let's get right into it and perform a typical first processing step like filtering. So I have the raw data activated. It's shown on the right here. Filtering can be found under transformations, artifact rejection reduction, data filtering, and I choose the IRR filters. In this dialog, I can set the high and low cutoff frequencies. Let me change these default values to say 0.5 up to 40 Hertz, for example. And of course, as you might know, digital filters cannot be perfect regarding the cutoffs, but ensure a certain suppression level at these frequencies. You can see in the right part of the dialog the filter response function. Slopes are shown in correspondence to the filter settings. So if I change the filter order, for example, you instantly see the changes of the filter response function. More detailed information about filters can be found in the user manual. Note, Analyzer works based on on-demand calculations. For filters, we recommend to use the cache option here to optimize filter quality. Filters can also be applied to individual channels using the lower part of the dialog. You select OK and the data is being processed. As you can see in the primary history file explorer up here, below the raw data node, we now have a node called filters. This is a special concept in Analyzer. Each processing step is represented in a dedicated node, which allows you to have a complete representation of all steps in form of a history tree. You may have noticed we now have also a second view showing the filtered data. This is the result of the filter transformation. Every time a node is computed and added to the history tree, the respective visualization is also shown. Going back to this tab, the raw data is shown again. It would now be interesting to see what exactly has changed in the filter step. In Analyzer, this is very easy to do. Let's first look, say, at the filtered data, and to compare this with the raw data, you simply go to raw data, use your left mouse button, click it and hold it, and then drag it onto the view. This creates an overlay. Let me just decrease the number of channels shown and rescale it also a little bit, so you can nicely inspect what the filter has actually done to the data. To get back to the filtered data again, you can simply click Clear Overlays. Let's apply another processing step based on the filtered data. Let me show some more channels again. Let's assume we would like to change the sampling rate. In Analyzer, this can be found or done via transformations, dataset, pre-processing, change sampling rate. When I start the transformation, I get a dialog in which I'm requested to enter the new desired sampling rate. For your convenience, the current sampling rate is also shown. Let's choose a sampling rate of 250 using the spline interpolation and pressing OK. Again, an additional node is created and it's called Change Sampling Rate. Also on the right, you see the new dedicated view. Now I would like to show you how to get more details about individual nodes in the history tree. For that, simply right-click on a node, and from the context menu you will see options like rename, or you can delete a node even. We recommend to change the default names of nodes to provide easier access to the information. Also, different conditions can be reflected in the node names. In this example, let's rename the filter node and give some information about what we did. So I enter here our cutoff frequencies, 0.05 to 40 Hertz. I press enter and a new name is given. In the same way, I'm changing or renaming the name of change sampling rate and just add 250 Hertz. Pressing enter and we have a new name. For example, if you right-click the node again, you find operation infos in the context menu. This is to display a summary of the settings that were used when the transformation was applied. Here, for example, the cutoff frequencies and the filter order that we set in the dialog. So every time you need to look up how exactly a transformation was performed, this would be the place to look at. Likewise, for each node, you can have access to the node properties. Node properties show you or give you information about the number of channels, the sampling rate, as well as the length of the data set in sampling points or in seconds. What if you're not happy with the result using certain parameters in a transformation? Or maybe you want to compare the results when using different parameters. This can easily be done using the Edit Parameters, Reprocess, and Copy options. So I again right-click on the node, and down here I find Edit Parameters, Reprocess, and Edit Parameters, Copy. The reprocess option will show the dialogues with the settings you entered before, but you will be able to adapt these parameters as desired. In reprocess, the current node with the results using the new the node is just updated, so no new node is created, but it's just replaced by the node with new settings. In contrast to the copy option, this will add a node containing the results using the new settings. This can then be used to compare the results in an overlay as we created before. So reprocess just replaces a node with new settings, and copy adds a new node with new settings. As you have seen so far, activating a node by double-clicking on it opens a dedicated view, and you will be able to apply transformations to this data. Now let's imagine that I would like to have access to other visualization options. When I right-click anywhere in the View window, from our context menu, I'm able to select Switch View. As you can see, different views are shown. Not all views are available because not all kinds of views are applicable to all kinds of data types. For example, select 3D Head View. By default, 4 head shapes are shown, which represent the topographic activity distribution across electrodes, projected on a standard head shape. For a single head shape, right-click again on the view, and you have access to the view settings. I can here, for example, select the number of maps and reduce it to 1. And by clicking on Apply, I will instantly see the changes. So every time you would like to make changes to the current view of a specific node, right-click on the view and select the respective view settings. Under File, Configuration, you even have Global View Settings, which changes the settings of views permanently. If you want to go back to your standard view from before, just right-click again, go to Switch View, and you find the standard view down here. For a quick view on the data and to further inspect the data, you can use the so-called transient views. You can select an area on the view with your left mouse button, pressing it down, and then just moving it along and select an area. The context menu will open, which you can also access if you have already marked an area, access via the right click again, and you will find transient views. For transient views, let's pick the FFT. And for each channel, an FFT spectrum is shown. I will quickly rescale it a little bit, and only by, again, left-clicking on the labels, just select a few electrodes for a better overview. Double-clicking will open this set of electrodes, and again, can rescale a little bit. And I can also move along time and see how the spectrum evolves over time. So this is a nice option to further inspect your data. So in short, again, Switch View allows to see the data stored in a node using different graphical displays. Transient views allow to compute transformations using only the data points selected by you. Now this output is transient, so it is not stored anywhere and no new node is created. And with that, let's move on to our last topic of this analyzer introduction, automatic processing. What if you would like to apply a sequence of steps to other data sets? When I click on the plus of the book icon here of subject 2, I have again access to the raw data of subject 2. Double-clicking it will open the dedicated view. If I now would like to apply the same sequence of steps to this raw data as I did for subject 1, there's a very fast and easy way to do this. What you do, you simply take the filters node, left click, hold it pressed, and just drag it onto the raw data node of subject 2. If I release the mouse button, you will see that the same processing steps are applied automatically, one after another, as we applied manually for the first subject. Afterwards, I can click again on each node to have access to the data. If the right side of the screen is getting very crowded up here with views, there's an easy way to clear this up. From the toolbar, select Windows and then select Close All, and all windows will be closed. As soon as you double-click somewhere on any node, it will open with a dedicated view again. So this was drag and drop. Now imagine you have a new dataset which needs to be added to the workspace and processed in the same way as the other two subjects. For this, to load a new dataset, allow me to minimize Analyzer shortly. And I assume in the meanwhile we recorded subject 3, and I'm just adding it to the raw data folder. Let me use this opportunity to show you the content of the history file folder. This is not empty anymore, but when loading data, Analyzer created dedicated history files for each raw file. These files contain all the information about processing steps applied. They have the same name of the raw data file, and as the raw files, they are also internally linked. Therefore, we do not recommend to rename or move these files. Going back to the raw data folder, as you can see, they have not been changed. This is a big advantage of Analyzer and is in fact one of Analyzer's top rules. Never touch or overwrite the raw data. The export folder is still empty. And this is simply because we haven't applied any export transformation yet. So let's go back to Analyzer. Via File, Workspace, I can press Refresh and Analyzer looks for new datasets. And as you can see, it appears here. Subject 3 is now added to the History File Explorer. Clicking on the plus sign, double-clicking raw data, I have access to that data. What I would like to show you next is how to create a history template, which we can use to apply the same processing steps to the new history file as we did for the other two. As said before, this is one of the most appreciated functionalities in Analyzer. We have a dedicated menu up here, and if I select New, here on the right, a new template is shown, which is empty at first, but only contains a root node. In order to create a template, I can again use the drag and drop functionality to include a certain processing tree in the template. Let's assume we would like to create from our mini processing tree here a template. I drag it onto and drop it onto the root node, and it appears in here. Now I have two processing steps in the template, and if I right click on each node, I can again check the operation infos and inspect what is actually done in each step. If I'm happy with the processing step stored in the template, I can now save my template let's call it demo. It's saved as an EHTP file and click OK or save. In order to apply this template now to subject 3, I go to history template and apply to history files. In this dialog, I can select the template. Currently, demo EHTP is still open, so it's selected automatically, but you can browse here for any other templates. I would like to apply the template to my raw data node, and I would also like the log file option. The nice thing about the log file option is that the template will continue to be applied even though for some reason a processing step could not be applied. For example, due to missing markers in a particular dataset. This ensures that you're not returning from your coffee break while you thought Analyzer was processing dozens of datasets but stopped after the second or third step. No, it will jump over a failed transformation and report this in a template log report. Finally, I need to select the history file. In this case, subject 1 and 2 were already processed, and I only need to add subject 3 to the selected file list. Pressing OK, this template will be applied, and as you can see step by step, the new nodes created for subject 3 as well. The log report says no errors, and this is a very efficient way to process your data, especially when you imagine you have recorded a lot of data sets. And again, by double clicking, you can inspect each step. And with this, I would like to finish part 1 of this webinar, and I hope you were able to follow me during our tour through Analyzer, its main concepts and functionalities. For a quick summary, let me go back to my slides. So to summarize, under the transformations menu, we saw that Analyzer offers a great range of functionalities to process EEG data in time, frequency, and time frequency domain. To demonstrate the main concepts, I only showed you filter and change sampling rate. To start working with EEG data, we created a new workspace and learned what's behind this concept. Remember, a workspace consists of 3 dedicated folders for raw data, history files, and export files. Raw data files are never overwritten. The processing steps are always stored in the history files. We learned about the concepts of nodes and the history tree in Analyzer. Every single function applied to the EEG data is represented as a new node in a tree structure. The settings used to create a certain output are logged in the operation infos of the node. This and many other functionalities can be accessed via right-clicking. Output values are automatically visualized using dedicated views. I showed different views that allow you to inspect your data in different ways. Remember the 3D head view as a switch to a view and FFT in a transient view. To efficiently process a number of data sets, history templates can be created based on history trees. Simply create a history tree for an example dataset, save it as a history template, and apply it to all other datasets automatically. Of course, history trees are usually more complex than the one I've showed you in this example. In part 2, I would like to give you an overview of the most basic concepts in EEG analysis to get a better idea of which way to go when you start analyzing your data. The reason why people may get lost in the very beginning is because of the complexity of the time signal itself. It can be represented by several domains. Most straightforward is the time domain, of course, the measured voltage values over time. This can also be transformed to the frequency domain, which is the amplitude or power over frequencies. The EEG spectrum has large values for lower frequencies and smaller values for higher frequencies. A combination of these two domains is the time-frequency domain, which tells us something about the signal amplitudes, here color-coded, over time, and at the same time about frequency. In addition, we know about the locations from which we record the electrode space. With some assumption, we can even localize the source underneath the source space. The last domain we can have a look at is either the activity at individual locations, or we can analyze how different areas are functionally related, analyzing the brain connectivity. In EEG analysis, the goal is to find the right method for your research question. As mentioned before, from the signals you record, you can get information about the location, about time, frequency, and also connectivity. The question is, what kind of effect am I looking for, and by which method is it best revealed? Is the effect time-locked to an event, or is it rather static, represented by the brain state? Do I expect transient changes in specific frequency bands? Do I need an estimation of the source of the activity to answer my research question? Or do I want to look at the brain as a network and measure functional relations between locations? All these questions we try to put in a simplified flowchart, which I would like to go through with you. I would like to introduce some ideas about experimental paradigms, what to consider for electrode space or source space analysis, and the different methods for different kinds of signal domains. For each method, I will talk about the motivation for why doing it, what it actually is, and what the result will be. Furthermore, I will show an example pipeline in Analyzer, and I picked out some example publications which use these methods implemented in Analyzer. Please understand, in this webinar we can only give very basic information on each point, so rather see this as a teaser for going further into the topics. Also, please consider this when addressing questions at the end. Further reading is required to carry out the demonstrated analysis. Please also check regularly for upcoming webinars featuring these topics. Let's start with differentiation between two basic paradigm designs: trial-based or event-related paradigms and block design for analyzing brain states. Up here you see a continuous EEG signal of one channel as it is recorded. In event-related paradigms, it is very important to get accurate markers indicating the events. Here we have two types of markers. In red, stimulus markers A and stimulus B, indicating the onset of a stimuli, like displaying a picture on screen or playing a sound to the subject. In green, we have response markers, which indicate whether a subject responded to a stimulus. This could, for example, be a button press. Here, one trial consists of a stimulus marker and its corresponding response marker, if it is there. It is obvious that marker coding is important to identify the markers correctly. In Analyzer, this is done by the marker type and its description. An aspect you will also think about in event-related paradigms is the number of trials you need, as well as the time between trials. To avoid systematic errors like learning effects, you would probably randomize the order of trials, which makes marker coding even more important. In a block design, we have different conditions or tasks to distinguish. Here this is indicated by one part of the EEG channel shown in green for condition A and in blue for condition B. They are separated by start and end markers, which we can use in Analyzer to separate these conditions. As in event-related paradigms, length of blocks and the number of blocks may be important, as well as a randomization. On the one hand, you need enough data to get a representative picture of the condition. On the other hand, you need to consider for how long you can get a stable recording and subject can actually engage in the task. Let's think about whether to analyze the data based on the electrode signal or based on estimated source signals. There are several things what to consider when going from source to electrode space and back. The recorded EEG represents firing neuronal assemblies in the brain. Their activity is passing through the different tissues of the head, which can be seen as a volume conductor. The activity reaches the head surface and can be recorded as the EEG as we know it. If you want to model this process, you need the location of a firing source in the brain and a good description of the head and its conductive properties, the head model. The result would lead to the EEG signal. This process is described as solving the forward problem. The other way around is what we call solving the inverse problem. Without going into detail here, what we do is we try to find the sources in the brain which would be best describe our EEG signal on the scalp level based on the head model we choose. I know this might be a bit abstract. If you're interested, I recommend to do some further reading on this. However, a few basic things need to be considered for working on the electrode signals or going to the source space. For source analysis, you need a large number of electrodes distributed over the scalp to get a good coverage. Often you will find a minimum of about 64 electrodes recommended. Secondly, the head model needs to be chosen. The closer the model is to the physics of the subject's head, the better the source localization will be. Furthermore, the actual electrode positions on the head must be known with respect to the head model. In electrode space, the number of electrodes is determined by the research question. This also applies to the distribution of electrodes. Typically, a 10-20 system or some extension of that is used. To make sure electrodes are positioned where expected, the right cap size and fit must be used. Knowing some basics about paradigms and electrodes or source-based considerations, let's talk about the signal domains and associated analysis method as implemented in Analyzer 2. We start with the time domain analysis in event-related paradigms and how to get to the event-related potential. Imagine your data is already segmented according to markers, let's call them X and O. The ERP is gained by averaging segments from each condition separately. You get an ERP for condition X and also O. What you can see are typical ERP components like the P3. A positive deflection from baseline around 400 milliseconds in this case. Different ERP components at certain locations have specific brain processes associated to them. You can notice in this example that the P3 here differs in amplitude and also in latency. Typically, you would do an ERP analysis if you expect an effect to be time-locked to an event and that conditions or groups show differences in latency or in amplitude of ERP components. An ERP represents the summation of local synchronized neural activity over time related to an event. It is contained in each trial, but revealed by averaging across trials to cancel out the noise. In the end, I get amplitude and latency values of ERP components, as well as topographic maps, showing the distribution of components across electrodes. Let's have a look how this is done in Analyzer. So I'm gonna switch back to Analyzer. And for this, I actually prepared a dedicated workspace. And just a note, all processing pipelines shown today are examples only and can look very different in other cases. Unfortunately, there's no such thing as one standard pipeline for a method. I open the history tree, the processing pipeline for ERP, by right-clicking on the book icon and then expand all. Shown here is an ERP processing pipeline for an oddball paradigm. Let me quickly walk you through it by mentioning the most critical points. After pre-processing, including filtering and also getting rid of EEG artifacts by ocular correction ICA, the continuous data is segmented to all conditions included for the auditory oddball task. Data is then baseline corrected and once more artifact rejected. And finally, because the oddball paradigm consists of two conditions, the frequent and the rare, we have a segmentation for separating audio frequent stimuli or trials to segmentation here, the rare trials. To get the ERP for each condition, we applied the average transformation for frequent and rare. The stronger response is expected for the rare condition. Let's look at it. I will scale up a bit and also maybe overlay it with the frequent condition. Let's, for example, look at electrode P3, and the difference is, for example, seen here around 400 milliseconds. So what I can actually do is just left click here, roughly at around 400 milliseconds. A context menu opens showing my options for transient views. And now I will click on mapping view. This shows nicely the distribution of this ERP component at this specific time point across electrodes. Again, I can even move the marked area along time and see how the distribution evolves over time. Going back to the slides again. Here's an example publication in which Analyzer was used for analysis. What is shown here on the left are ERPs for two conditions. And they are overlaid just like we did in Analyzer. On the right, you see the difference wave of these two conditions and a topographic representation of that as well. Please note, this publication and following ones are examples only for cases where Analyzer was used. They are not selected based on any other criteria, and I'm sure you will come across many more papers when you do your literature research. Let us have a look into the frequency domain, which is used to analyze brain states. A block design is often used to analyze task differences. The continuous data is here segmented in consecutive intervals before going to the frequency domain. FFT is then calculated for each segment and averaged as a last step. Of course, an FFT could also be calculated for the whole time of a block, but due to the stochastic nature of the signal, the resulting spectrum might not be representative. The spectrum is therefore stabilized by calculating the averages across many segments, as shown here. FFT is done when oscillatory effects are expected and to get a spectral characterization of a quasi-static brain state. The average spectrum represents the activity of neural oscillators per frequency along the comparison between conditions or tasks. From the frequency spectrum, you can get the voltage or power values per frequency as complex or non-complex values. Additionally, you can look at the distribution of specific frequencies or frequency bands across electrodes. And to show this again, I'm going back to Analyzer, closing the ERP history tree and opening the one for FFT. In this example, a conditional segmentation was done to separate a resting eyes open from a resting eyes closed condition. So here's segmentation for eyes open and eyes closed. Those of you who know the Berger effect already expect to see a sharp peak in the frequency spectrum around 10 Hz for the eyes closed condition. As mentioned before, a segmentation or subsegmentation here of 2 seconds was done. 2 seconds will result in a 0.5 Hz frequency resolution. After that, FFT is calculated for each segment separately in both conditions. The final step is to apply the average transformation to get a stable frequency spectrum for both eyes open and eyes closed. Let's check out the eyes closed condition. And let me pick, for example, electrode P7 by double-clicking on the label. It enlarges, and let me rescale also a bit smaller. As you can easily see here, a clear 10 Hz peak is shown as expected. And what I can do again to further inspect, I can mark this left mouse button, drag it along frequencies now to mark this alpha frequency band. And I again select mapping view, down here exactly. And this allows me to inspect the distribution of this frequency band across electrodes. The Berger effect is mostly represented in occipital electrodes. Here's another publication showing eyes open and closed conditions in 2 groups of stroke patients and a control group before and after some kind of neurofeedback training. Note the parietal or occipital location of the effect is also shown here as we saw it in Analyzer. Next, let us have a look into the time frequency domain, which is used to show transient effects which are specific to certain frequencies. It can also be applied to block design data, but is best demonstrated on data showing event-related activity. Time frequency panes are most often shown as color-coded values across time and frequency. This figure nicely shows the benefits of time frequency analysis, here using wavelets. Again, we have segmented data, time locked to some stimulus. And below you see the ERP. This shows major deflections around 100 milliseconds. Please note the activity between 200 and 300 milliseconds, as shown in the single segments, is called induced activity, but it is cancelled out due to the averaging in the ERP, like you can notice down here. Looking at the ERP in the time frequency domain shows the so-called evoked activity around 100 milliseconds. It is around 40 Hertz, which is why the label here says evoked gamma. Because the wavelet is calculated based on the ERP, the induced activity does not appear in here as well. A different approach is to calculate wavelets on the single segments first, and then take the average of those time frequency panes. This actually contains both evoked and induced activity, but the activity around 100 milliseconds is not as strong. Marked here is induced gamma only. Again, for those who never came across time frequency analysis, this might be a bit quick, but a bit of reading into the topic will surely help to understand. So why are we doing wavelets? Basically, when effects are expected to be transient in time and frequency specific. Time frequency analysis reveals the dynamics and local activity of neural oscillators in time and frequency during event-related or continuous paradigms. And instead of time or frequency information only, we get both in combination. For each frequency bin, we can get the voltage, power values, or values as complex coefficients. As with the other methods, also here we can look at the topographic distribution. And again, I'm going back to Analyzer, closing FFT and expanding all steps from the history tree of my wavelets dataset. This history tree was built on the same data I presented for calculating the ERPs. As you can see, after segmenting into each condition, frequent and rare, the wavelets transform is applied to each segment and then averaged. Yeah, let's just check the result here. Maybe, yeah, this is a bit better to inspect. And choose, for example, Electrode P3 again. Double-clicking on it will open the time and frequency view for Electrode P3. And here we can invest by again placing or clicking with the left mouse button in the field and dragging it along. We can inspect nicely this transient dynamics, specific around 10 Hertz, and then changing over time. Down here, we get a topographic distribution. In this publication, the authors used Analyzer to show both the time frequency plot of the 3 age groups and the topographic maps for different frequencies in a learning task. The time frequency plot shows the result as presented in Analyzer just now as both evoked and induced activity. Now let's have a look what can be done in terms of source localization in Analyzer 2. The algorithm implemented is LORETA and is acting pointwise or as an average across a selected time interval. If you will, there are two ways to look at LORETA results. One is to find the location of a source being active in a certain time interval. LORETA assumes distributed sources, which is why you see these patches highlighted. In contrast to this, there are techniques which, for example, assume point-like sources. Here the activity is localized in the parietal to occipital lobe. The second way is to look at the estimated source signal, the activity over time estimated at a specific location. Here lateral Brodmann areas BA17 left and right are shown. So if your research question entails the estimation of sources because it asks to localize an effect, LORETA can help you do this. On the other hand, you might have a hypothesis which tells you which area shows an effect most prominently, which is why you would look at the source signal. LORETA offers a solution for estimating distributed sources based on the assumption that the sources have a smooth distribution. As presented on the left, what you get is either the location of maximal activity in a specific time interval, or mean current density, or as power within a region of interest. You can even get the source activity for each X, Y, and Z component separately. Also for LORETA, I have a history tree prepared. And basically what is done here is an ERP pipeline, which ends with an average. Rescaling a bit, shows me a nice deflection here. And if I click on an ERP component, I can, from the transient views, I can select LORETA. This shows you an estimate of where the sources of the component, which you just picked, is located. At the bottom, it even shows you the point of maximal current density, right here. And also, it names the closest Brodmann area. By dragging the marked area along time, you see how LORETA estimates the source locations for each point in time. Knowing where to look, or based on your hypothesis, the LORETA transformation allows me to estimate the source signal at this location. This is done here in the LORETA step. This one I need to scale up a little bit. In this case, the source signal for BA17 again, left and right, was estimated and shown as a result. And of course, you can not only choose one region of interest, here the BA17, but also several regions of interest at the same time. In this study, published in 2014 using analyzers LORETA, a very similar source was identified. This is a fMRI EEG study. The special thing about this combined studies is that you have information from both modalities complementing each other. The very high spatial resolution of fMRI and the high time resolution of EEG based on different kinds of signals. As a last method, let me introduce the concept of connectivity analysis in Analyzer 2. Currently, coherence and measures of correlation can be used. The concept of analyzing brain connectivity is all about not looking at signals at each individual location, but at dependencies between locations. In brain connectivity, you will find three different modalities. First, structural connectivity looks at the physical connections between locations. This can not be done by EEG, obviously. As illustrated here, functional connectivity describes functionally related regions. It is said to be non-directional because we can say which signals are related to each other, but not which signal influences the other one. This is possible with effective connectivity, which aims to reveal the causal relations between the signals. In Analyzer, functional connectivity measures coherence and correlation is implemented. So, what is coherence? In simple words, two signals 1 and 2 are said to be coherent if they oscillate with the same frequency and a constant phase angle. The result of coherence of the coherence transformation, also in Analyzer, shows a spectrum, here indicating a coherence which is 1 at exactly 10 Hertz, which in the case of EEG could then indicate a functional relationship. Connectivity analysis is used when the functional relations between channels shall be analyzed, or your hypothesis expects a condition or group effect to be manifested in functional dependencies. Coherence and correlation are both measures of the degree of linear dependencies between two signals. As implemented in Analyzer, coherence is a measure of how coherent two signals are per frequency and across segments. Also, the correlation transformation can be seen as a stability measure of inter-channel dependency across segments. And let me finally go to Analyzer again and show you the history tree for coherence, which I prepared. Again, the auditory oddball data is taken here, but the pipeline is actually very similar to the one for frequency analysis. Note that the coherence is applied to FFT, calculated on single segments as voltage and with complex output. As mentioned before, coherence calculates averages across segments itself, so no average transformation is needed. Let's have a look at the rare condition, for example. The result is displayed in frequency spectra with coherence values on the y-axis. The view can be changed again by right-clicking and then using switch view to a band channel pair view. This is showing coherence values between electrodes, color-coded per predefined frequency band. Delta bands, theta, alpha, and beta. In this study, FFT power and also coherence was calculated in different patient groups, measured during a resting state. This figure shows the coherence values from 0 to 0.2 in delta and 2 alpha frequency bands as channel pair maps. The line strength and color indicate the coherence values between electrodes. Sorry. And with that, I finish our tour through EEG analysis concepts, and I hope you got a good orientation about which ways you can go. Let me summarize. Your research questions determines the experimental design, may it be event-locked or in a block design. You should consider whether to work on electrode signals or if you do source localization. And it determines the analysis approach to be used. More complex research questions may even require several approaches, which can easily be done in parallel processing trees in Analyzer. As we could only give brief introductions to the methods, I recommend to start reading further in textbooks or peer publications to further get into the details of these methods. Where do you find more information? Please consult the user manual when you have questions about Analyzer. The manual can be downloaded from our website and is installed with and accessible from within Analyzer. Secondly, for many topics, we have very useful press release articles and support tips which may contain just the correct information you need. Check it out on our website. For general questions, we would also recommend to start reading in books covering the EEG-specific processing methods. And of course, a good starting point are always the publications related to your field of research. As you might have seen before from the transformations menu in Analyzer, Analyzer has much more transformations to offer. We have a single trial feature export. We have magnetic resonance artifact correction as well as cardioballistic artifact correction if you recorded data in an MR environment. We have basic processing for electromyogram, electrocardiogram, galvanic skin response signals. You can import certain kinds of eye tracking data. You can do your independent component analysis as well as cross-correlation or event-related synchronization or desynchronization. And of course, as you have seen, many more. And with it, if you haven't done already, we now invite you to ask questions regarding the content. Please address all content-related questions to the moderators via the questions pane. Please note that in case we get a lot of questions, I may not be able to answer all of them. So I see a few questions already came in. And one is, where exactly can I find out which data formats can be read by Analyzer? For that, let me show you our website. There we go. No. Here we go. Go to products. By name to find Analyzer. And under technical specifications, you can check out all the transformations, views, and here you have a list of all the data formats, all the readers which are implemented. Okay. What else do we have? Okay. Can you show how to export single trials for particular channels within a specific time window? Okay, the question also goes a bit on. Allow me to just answer the first part and let's see how far we get with that. Let's go to Analyzer. Okay. Single trials and specific time window. Okay, let's go to the ERP pipeline. Maybe showing single trials, so I select the segmentation. Down here you see segments 1 of 70. And as I said, single trial analysis is mainly reflected in our solutions, and you were asking for the export. I mentioned the peak export before. Oops, it's running on the other screen again. What you can do here is you can actually also not only do the peak export or export related to peak information, but also select a time area. You can select a start time and a stop time. It actually gives you the times which are actually available from also your time resolution, so sampling rate. You can have some baseline settings, normalization, so you can calculate the area under the curve or the mean, and you can select all channels or specific channels. You select your output file and then just press OK. You will find this file, a TXT file, in your export folder of your workspace. If you want more information, and maybe I show this very quickly regarding any transformation, what you can do is go to Solutions Help, navigate to your solution of interest, peak information, and just double click this. And sorry, here we go. Okay, and you will get a window with all the explanations for all parameters. So if you're not sure what kind of parameters you want to set or what it means, this is a place to look for. Yes, and this will, again, the important thing of this question was, I guess, to export the single, on the single try level, this will export for each and every segment of the 70 segments, the output measure you selected from that time range. Okay. There's another interesting question. How many channels are needed for coherence analysis? Are 32 channels enough? If you're doing coherence analysis based or in the electrode space, so based on the electrode signals, the number of electrodes actually don't matter itself, because what you do is you calculate coherence between two signals, or 3 or 4 or 5. So there's no minimum number of channels you need. The minimum number of channels you need might arise from some other processing or pre-processing steps you used before. So for example, if you wanted to do ICA to clean your data before, then we always recommend to have more channels, and 32 is actually quite hard to answer regarding ICA. Also goes into a different topic a bit, but basically ICA needs as much data as possible, so more channels are better. Depending on what kind of components you want to reject, 32 might just be enough. But otherwise, regarding coherence, you can just also have 2 channels and calculate it between those. There's a nice question. When you were showing the head maps of the wavelets, was that for one participant? How can we get an average of all participants? How does the output function work so that we can actually analyze those? Okay, this is very important actually, because what you want to have in the end is of course a grand average across your subjects. So of course this workspace is not really suitable for showing it, but I can do it in theory. Imagine you have all your subjects in here and you process them in the same way. You mentioned wavelets, and yes, this was just for one subject, for all channels for this subjects, and then I showed, I guess, this one here. For a grand average, you find under transformations and result evaluation up here, our grand average. I can only briefly explain, but what you do is you enter the nodes you want to include in your grand average. So for example, well, I would have named it actually average audio rare, for example. You include it here and you specify your output file. So for example, grand average audio rare. You select all the history files you want to include and then calculate the grand average. What will happen afterwards, grand average is a secondary transformation, or in other words, it produces a history file in the secondary tab here, down here, secondary history file explorer. So once a grand average is calculated, you will find the result in here. And there you have access to the data, just like it is shown here. And you can inspect it based on the grand average. And if I understand correctly, the last part of your question, actually analyze, how does the output function work so that we can actually analyze those? If this analyze refers to the statistics, well, for wavelet specific, you would first need to define what exactly do you want to export. A specific time range? Do you want to average across time range? Do you want to average across frequencies? So what people would do, for example, based on a hypothesis, for example, they know some kind of time area and also frequency range. And by using, for example, wavelet layer extraction, you can reduce to a certain layer of the wavelet. And then using export the area information, because after reducing the frequency domain to one layer, you can then select a certain time range. Let's say here, I don't know, 0 to 200. You would here give the node names of what you want to export, and again you include all the history files you want to include in the export. You can also set an area or mean activity again, and it will write to the export folder as a txt file. So what you get is, of course, you do this on based on each subject, so not on the grand average, because statistics you obviously calculate based on the subject results. So what you will find in this txt file is for each subject and channel and condition and so on, let's say a mean value between 0 and 200 from your prepared wavelet result. Again, after limiting to a certain wavelet layer, for example. I hope this answered your question. Okay, we're running out of time, and again, thank you all for your questions. If yours should not have been answered, please feel free to send us an email via support@brainproducts.com. I'm going back to my slides. Here we go. And for some final words, we would like to thank you for your participation and attention in this webinar. The slides are available as a PDF document. You will receive an email with a link to the video, and a survey is available directly after the webinar and also via a link in the follow-up email. And please, if you have any questions about the content of this webinar or also processing an analyzer too, please contact us under support@brainproducts.com. And with that, I'm saying goodbye also from behalf of my team, and happy processing.